Hi again, good afternoon. We will talk now about multi-microphone speech enhancement and specifically about some mechanism for source counting and speaker diarization, which are incorporated into the separation scheme. This is work that is related to a lot of works that we did along the years for, I would say, the last 10 years, and including work from the current year. So I'll try to do a brief overview of beamforming for speech processing and continue to the recent work. So I'll talk very briefly about array processing preliminaries, but I'll spend a bit more time about the differences for microphone array processing, and I will show that you should work with microphone array more carefully and take into account the entire propagation of the acoustic signal in real environments, and that if you take them properly into account, it gives you a lot of benefits. So after talking about this concept or about this new paradigm, I will talk about optimal beamforming, several criteria and their relation. And specifically, I will talk about beamformers that are taking into account the acoustic transfer function, more specifically the relative transfer function, which is related to it. I will explain about it later. Then I will take this concept and incorporate them into a beamforming scheme, which works with multiple speakers that are speaking concurrently, and sometimes like more natural type of conversation. So people will stop speaking once in a while, and this is why we need also diarization, and also we will discuss about masking. I guess that section number 6, which is relatively long, will be in the next meeting. So let's continue. And first, a very brief introduction. Why do we need the microphone arrays? So there are multiple applications, including hands-free communication, teleconferencing, which we are doing now. Hearing aids uses microphone arrays in recent years, usually 4 up to 6 microphones. Eavesdropping, like police type of application, is very important. And very fastly growing applications is smart homes, smart cars, smart environment in general, in which you speak to your devices and the devices are listening or understanding and apply actions due to the sound that they recognize. And robot audition, of course, which is the main core of our project. So microphone arrays can be found anywhere, and most devices, new devices, will have microphones. So there are computers, cellular phones, dedicated microphone array, and also very huge microphone arrays, which of course we will not use in this project. And actually, one of the claims is that we do not need so many microphones when we work in the new paradigm which we are proposing, which takes into account the acoustic propagation. The fact that the acoustic propagation is taken into account helps us a lot in improving the beamforming and also to increase the spatial resolution of the beamformer. So microphone arrays, actually, I would say that the major revolution was these home assistant devices like Amazon Alexa, Google Home, HomePod, Cortana of Microsoft. So all of these devices gave a huge boost to the microphone array industry and also to the microphone array industry, of course, together with a lot of new developments in the algorithmic domain, which I will discuss later. So although we are using microphone array, well, array processing is from more or less World War I, but microphone arrays in the late 80s, maybe 90s, people started to do some research on this topic. And together with this, some development in hardware that allowed us to integrate a lot of microphones together. So this is not a new era anymore, the microphone arrays, but I would say that the real boost is from the last 5 years. Okay, so I will try to explore very, very briefly families of algorithms which are using spatial noise reduction or speaker separation. So some of them, maybe the more classical ones, is the fixed beamforming, in which you direct a beam towards a specific direction of interest. These are usually called data independent, so you design them in advance. So they should be in a very controlled environment. Perhaps very important contribution is the work from 1996 by Yamin Flanagan, which used a huge microphone array, several hundreds of microphones. This is, of course, not something which is applicable in daily life or in home environment. Another family of algorithm will be the blind source separation family, which encompasses several types of algorithms, especially I would say the independent component analysis, so imposing independence between the signals with a lot of versions, second order and higher orders. Some of them are listed here. Other algorithms which are also related to this concept are the non-negative matrix factorization, independent not component analysis, vector analysis, which is an extension of the independent component analysis, in which all the frequency beams are treated together. And maybe Ilerma is the most important contribution in this field, which is very recent work and working very, very nicely. And computationally auditory signal analysis is something that try to imitate what we are doing as people, is something that emerged in the beginning of the 2000s, but I would say that it's now not working as a standalone algorithm, but some of the concepts are integrated in many of the other algorithms. The main family of algorithms that we'll discuss here are part of the family of adaptive beamforming, and in the next slide we list several criteria. About minimum variance, distortionless, especially the general silo canceller, Wiener filtering, maximum SNR, and so on. I will discuss all of them later. You have here a list of several important references. By no means it's a comprehensive list, but still gives you a lot of algorithms, and they are all listed at the end of the presentation. In recent years, I would say 2010 and on, or even a bit later, deep learning emerged into the beamforming domain. I will discuss or maybe mention some deep learning method, but there are a lot of other beamforming methods which are based on DNN, which are fully DNN. There are several ways to integrate deep neural network. One of the ways is to use them as a control to the beamforming. I will discuss this briefly. But other methods which are very, very new try to implement everything via the learning paradigm. I think it's a very emerging field, and we should keep looking at the literature. I don't think that still these methods are providing the best results, but I think they are fastly emerging, and it's something that we should pay a lot of attention to it. Here is a list. I would not go into the list. A list of books and survey papers that from the last 20 years, I would say. Especially in the last few years, there are several surveys and books on the field, which you can use in order to see a bit of a comprehensive tutorial style contributions on the field. So, but I would not get into it, and we can continue. So a very brief introduction of what is array processing. So array processing is actually multiple filters that are applied spatially, namely to each microphone separately, and then the output is summed to provide an output, which is hopefully enhanced in some way, and we'll discuss multiple criteria how to enhance the signal. So this is M-to-1 filtering paradigm, here written in the time domain, but usually we apply it in the time frequency domain. In the next slide, we will see the most commonly used array processing paradigm in which the filter is designed to distinguish between direction of arrival. So you can see that there are waves that are coming towards the array. There is a delay between the rays or the acoustic propagation or the propagation due to the angle of arrival. And then we can see it will not get into it too much, that actually the array response is the spatial Fourier transform of the array coefficients. In the next slide, we see a very famous member of this family of algorithms, which is the delay and sum beamformer. And you can see a beam pattern of the delay and sum beamformer. It actually directs a beam towards a certain direction, here 40 degrees, for instance. And there are side lobes, but there are not any specific care not any specific measure in order to take care of the side lobes or the beam width or the separation capabilities. It's just directing a beam. So this is very classical beamformer, which we will not use in the algorithm, in the project. Now I would like to discuss, which is I would say an important topic, is what are the differences between array processing in general, the array processing in the free field communication, I would say, arena, and array processing in speech applications. So first of all, in speech application, we have very long multipass. So we have very long impulse response. We usually call it room impulse response, or in the frequency domain, acoustic transfer function, that relates the speakers and the ears of the microphones. You can see on the left-hand side a picture of the propagation. So when someone speaks in an environment, there is a direct pass from the mouth to the ears of the listener, but also a lot of other passes and sub-passes that comes from all facets of the room and also from all the objects of the room. This is a phenomenon that we usually refer to as reverberation. And on the right-hand side, you can see a typical impulse response. So you have depicted in blue the direct pass, then in green some early arrivals, and then you can see a very dense, exponentially decaying tail of a lot of impulses that are impinging the microphones from all surfaces, actually. And what you can see that we measure this in seconds. So you can see here, this is very typical to like I would say, small office, and this is 300 millisecond or 0.3 second, as you see here. And this means that the multipass or the length of this impulse response can be few thousands of taps if we work in 16 kilohertz sampling rate. So this means that we have a very severe multipass, and on top of this, it can be also time varying when the speaker is moving, even nodding his head, and especially when he's moving from one point to another within the environment. So we have a very long impulse response, although decaying, but still very long, and time varying. This will have a major influence on the speech quality. I would say especially on the recognition rate of the acoustic of the ASR, of automatic speech recognition systems, and this is why we'll need to take care of this reverberation, and of course we should take this into account while designing the beamforming. Next. So one thing that I would like to discuss is something which I call, in quotes, uncertainty principle. It's not the famous one, but it's related to it, I think. So it's related to the question of what will be the length of the frames in which we apply the short-time Fourier transform. So as I said before, when I introduce beamforming, we usually do not work in the time domain, but in some transform domain, usually in the short-time Fourier transform. Although in I would say last 2 years, we have also testnet, which is working in time domain, but I think it's still the major work will be in the short-time Fourier transform domain. Namely, the signal is cut into small frames, and each frame is transformed to the Fourier domain. And then usually there is some overlap between the frames, and this is where we do the processing. So one major question is how long should be these frames of the short-time Fourier transform? So in the left-hand side, I discuss long frames, and in the right-hand side, I discuss short frames, and I will discuss now the differences. So if the frames are very long, well, I would say longer than the impulse response, then the convolution with this room impulse response translates into multiplication in the frequency domain. So the multiplication of the frequency bins of the frame multiplied by the acoustic transfer function. And we call this multiplicative transfer function approximation. It is always approximation due to the some issues related to the short-time Fourier transform domain, which I will not discuss here. But in order to have real multiplication per frequency, you need very long frames, much longer actually than, or at least at the same order of magnitude as the impulse response. This imposes very long frames if the impulse response is few thousand taps. So we need frames which are few thousand, might be too long for real-time processing. However, the major benefit of using such long frame is that all point sources become directional, and all reflections that I discussed before are treated coherently. This gives us a lot of benefits in the way that we can direct a very narrow beam toward the source, and we can also direct a very narrow beam towards a point interference, like a air-conditioned computer or some noise source or another speaker, and then we can quite easily actually attenuate the interference and maintain the desired source. So these are the benefits of using very long frames, but of course there are a lot of drawbacks due to latency of the processing. On the other hand, if we work with short frames, as depicted in the right block, actually what is happening in each frame is that on top of the signal that is arriving in the specific frame, we also have a lot of other reflections that came, let's say, older parts of the speech that came from the reflection. So after the sound was reflected several times on the facets of the room, it will arrive at this frame and actually overlap the current frame. This is an overlapping phenomenon, but what is really important is the fact that these signals that are overlapping are coming from all directions, since they have already encountered a lot of reflections. So the fact that they are reflected from all directions makes the sound field very diffused. What we call it a diffuse sound field, and we cannot apply any coherent processing. This is why we might lose a lot of performance while doing this, and we cannot do coherent processing anymore. There is in this the lower gray box, there is some compromise that tries to work with short frames but still take into account coherent processing from previous frames, and this we call the convolutive transfer function approximation or compromise, in which we can apply the beamformers that we discussed, but not only in the current frame, but also using some past frames. This becomes a bit more involved, but more accurate. So this is a compromise that we should do. Okay, so now for the new paradigm that I would like to stress here. So rather than working with direction of arrival only, like the classical beamformer that were adapted from array processing, usually radar and communication, in a remote environment, we would like to work with the entire impulse response. And actually, we are saying that the angle of arrival is only one arrival out of multiple, maybe thousands of arrival. So we would not like to ignore them, since if we will do this, all of these reflections will actually become an interference source, and very severe interference source, which will not allow us to work properly. So the new paradigm that we would like to introduce here, a relatively new paradigm, is the fact that we want to take into account the entire impulse response in several ways. We'll discuss multiple ways in the next slides. So the first thing that we do, we generalize, or we substitute the classical steering vector, which is based on angle of arrival only, to the entire acoustic transfer function, or at least a major part of the acoustic transfer function that is enough for us in order to take advantage of these reflections. These acoustic transfer function actually summarizes all the arrivals, or at least the major part of the arrivals, and we treat them as a fingerprint that characterizes the specific position. Actually, this fingerprint is very specific to any position, and this is why we can have much better resolution if we are using these fingerprints rather than angle of arrival. As I mentioned in the beginning when I showed some beam patterns, I showed that the beam pattern can be quite wide. This is due to the limitation of the array size, actually. But the fact that we use a lot of reflections actually improves the resolution a lot, and this fingerprinting concept will allow us to design beamformers which have much better resolution with fewer microphones. After doing this and working per frequency, we are actually having a vector of arrivals which doesn't have a specific angle interpretation anymore, and we treat them as an abstract linear space, and we apply linear algebra method as I will do in the next slides. And these will allow us to design the beamformers in actually more natural way than working with this spatial Fourier transform that I discussed in the beginning. So in general, the classical paradigm that takes into account the direct path only in the orange left arm of this figure, and in purple we have beamformers that are trying to utilize the entire impulse response. I would say that we are willing to compromise and to use a major part of the impulse response and not the entire one, but still we want to use much more reflection than only the direct. So this is our paradigm, which we'll discuss in this talk and also in the project. So I will discuss now some of the criteria of multiple speaker, but first I want to have an official introduction of what we have here. So of course we have signals in the time domain. We transform them to the short time transform domain and have L and K, which are the frame and frequency indices. We have multiple desired sources. Their number is PD. It's the first summation. Then we have multiple interference sources, and then we have some ambient noise. And all of these signals are actually received by an M microphone array. And this is also written here in vector formulation. And in order to do the processing, we needed the number of desired sources plus the number of interference sources will be smaller than the number of microphones. Of course, we know that in regular environment, especially in the environment that we'll have in the project, we might have much more speakers, but here I depict only the speakers that are active and are interesting. All the other ambient noise or diffuse noise or bubble noise that we will hear will go to VM as non-coherent sources, which we'll discuss, which we will treat a bit separately and will not direct the beam towards them. So there are sources of interest. The number of them is P. It can change from frame to frame depending on the number of, or depending on their activity pattern. But the total number of sources that we would like to treat in a specific frame should be smaller than the number of microphones. And now we will have several criteria. I will not get too much into it, but I will start with actually, which is the main working horse of the algorithm that I'm presenting here, is the linearly constrained minimum variance beamformer. There is another version which is minimum power beamformer. And actually what is done here is to minimize the noise power at the output, subject to a set of linear constraints on the sources of interest. And this can have a closed form solution. You can see that there are two solutions, one which is called LCMV and one LCMP. The LCMV is using the noise power, so minimization of the noise. The LCMP is minimizing the entire power. I would say that if everything is fine and we know the constraints set exactly, then they are equivalent. Otherwise, the LCMP is much more sensitive to misestimation or wrong estimation of this relative transfer function that we'll discuss later, or the steering vector in general. In this slide, we have a specific or a special case of the LCMV beamformer in which we have only one source of interest. It doesn't say that there are not other sources in the system, but there is only one source of interest, and then we have one constraint. And then this matrix form becomes a ratio, which is written here in the red block, and at the output we'll have the desired source plus some hopefully small residual noise and interference signal. Another interesting idea is the speech distortion weighted multi-channel Wiener filter, which is a version of the Wiener filter which we'll explain in the next slide, in which in the regular Wiener filter we actually try to minimize the minimum mean square error between the desired source and the output of the beamformer, which has two terms. One of them is residual noise and the other one is distortion. The speech distortion weighted is actually adding this mu, which is a weight that weights or gives different importance to a distortion term, this one exactly, to a distortion term and to the noise term. And if we look at the solution, which is given in the last block, you can see that mu is here. But if we'll see, for instance, that mu is 0, we will have the MVDR beamformer exactly, since everything cancels out. If mu will be 1, we'll have the multi-channel Wiener filter. So all of them are part of a big happy family of beamformers. There is an extension that we proposed several years ago that gives weights to each of the sources of interest, and then this criteria generalizes actually the LCMV, the MVDR, the MWF, and the SDW MWF. It has its issues with the control parameters for each of the sources, but you can see that there are a few sliders that actually on one side we have much less distortion. The LCMV side we do not have any distortion to the sources of interest, and on the other side we have less noise. So the overall error is lower. So there is a trade-off, and there are several sliders, but I will not discuss this procedure further here in this talk. So let's discuss the RTF beamformer, which are important for me for the actual application of the beamformer. So let's start with something very simple. So I would like to have, let's start with the MVDR beamformer, in which I have one constraint, which is constraints towards the desired source. I have the acoustic transfer function from the source to the entire set of microphones, which is h of d. And then I have g tilde, which is rather than 1, as we did before, is the transfer function between the source and the reference microphone. So now the constraint set is given in the lower part of the blue box. But if we'll divide both parts by HD0, we actually have HD divided by HD0, which is nothing but a normalization of the transfer function from the source to all microphones, normalization by the reference microphone, and G becomes again 1. Now in the next slide, we'll start to explain why this is so important. So first of all, by doing this, we treat the source, the desired signal as received by the first microphone or the reference microphone as the desired source. So now we actually compromise or relax the reverberation requirement, and rather than separating the source itself, we separate the source, the clean source, as received by the microphone. This might be good, it's still, the reverberation is still there, but still it might be good in the fact that it gives us a better trade-off between noise reduction and reverberation, and it can allow us to do more noise reduction if we are not too much concerned with the reverberation. This RTF can be generalized to all beamformers that we discussed before. If we go back to the multiple speaker environment, then we have the set of sources HD. This is all the transfer function from the source to all, from all desired sources to all microphones. HI, which is the same for the interference sources. We would like to have a beam towards all the desired sources, so PD1s in G, and zeros to the all interference sources. This, if we apply this beamformer, we have actually a summation of an entire conversation at the output. This depends on the application. If it's an application of an automatic speech recognition, so we probably want to have each source separately. If it's an application of a conversation recording, we might have them all together. If they are polite people and don't concurrently speak, then maybe we would not like to really separate them and have each one of them in a different time slot during on one output. So it really depends on the application. What is interesting is that we do not have to exactly know all the transfer function, but we can rather have a basis that spans the subspace. So rather than directing a beam towards all specific sources, we can, in specific application at least, direct a beam towards the basis vector of these sources. And also for this, we can apply the same idea of normalization by the reference microphone, which is given in the modified block with this normalization by the diagonal element. And in that case, we have a summation rather of the sources as were created by the sources. We have a summation of the sources as received by the reference microphone. As I said before, this can give us benefits in performance. We do not need any calibration of the microphone positions or anything related to it. Of course, we have the issue of the fact that the beamformer that is working with the RTFs will have a lot of coefficient which we'll have to estimate. This is an issue. And any beamformer, I would say, but also we inherit this. If there are diffuse noise sources, like a lot of people in the environment, like in the waiting room, then in this case, we need to do further post-processing. Here is a list of a lot of post-processing algorithms. I will discuss another version at the end of the talk. So now we would like to need to estimate the RTFs, of course, and we need to estimate the correlation matrix in order to apply the algorithm. And maybe I will finish the talk by at least saying something about these RTFs in the next 2 slides, actually. So here we can see real impulse responses that were recorded in our lab. So in the left-hand side, you see 2 impulse responses, one in blue and one in green. And on the right-hand side, you see the ratio, actually the ratio in the time domain. So you see that there is a very pronounced peak, but there is a tail which is 2-sided tail. What is nice in this relative transfer function is the fact that we can estimate them blindly from the microphones. So rather than estimating the entire impulse response, which involves which involves a non-blind estimation procedure, we need to know what is the source in order to estimate the transfer function, which is of course impossible. Here with the relative transfer function, we do not need this. This is, I think, the major benefit of the relative transfer function, and this is what makes it applicable to real beamforming in real environments. It also generalizes the time difference of arrival beamformers. One small issue, it might be large, but it's here in the picture, it's not too severe, is the fact that we have since it's a ratio of two transfer function, we might have a response which is a bit non-causal. This is something that we should take into account, and it's giving us a bit of an annoying artifact sometimes, and also some latency. There are many algorithms to estimate the room impulse response from 2001 on. So the paper in 1996 was not in speech processing. So all these papers are dealing with RTF estimation. It's quite active field of research. I would not get into all of them, but some of them I will explain later when I will explain more specific algorithms. And this is exactly where I think I should stop. Maybe we can have a few questions. And in the next part, I will explain, I will go in details on a specific algorithm that also apply diarization and masking.